Have you ever wondered, why is that Avogadro's number? The number of atoms in a mole, why did it wind up such an odd number? Why isn't it just 1 septillion or 100 sextillion or 1 quintillion? Obviously, it had to be a big number, but why did it wind up being that number? Well, let's find out. First of all, the concept of measuring atoms in this way, also molecules in this way, was created by Amedeo Avogadro, the brilliant chemist who had a great idea. His name often gets confused with similar sounding names like avocado or abogado, but his name is Avogadro, and his idea was, how could we count atoms? That's basically it. How could we count molecules originally? How could we do it on our big scale? We can't see them. We can't measure them directly. Well, we got to count them in big groupings. By the way, can I just point out that he just simply has the best name ever. So I have tried over the years many different ways to describe what a mole is and why we use it. Here are some of them. The mole is Avogadro's number of some chemical. The mole is how we count chemicals. The mole is the only way to measure chemicals equally and fairly, not being biased. The mole brings measurements up to the macroscopic scale, the scale we live on, the scale we can measure. And the mole is like a way to count the otherwise uncountable. So that's how I try to describe it. There's many other ways. But let's see if this new one works better. So here is Avogadro's number, 6.02 times 10 to the 23rd atoms per mole. You could also use it if you're counting molecules. So you could have 6.02 times 10 to the 23rd molecules per mole, or any other particle. You could have 6.02 times 10 to the 23rd particles per mole. So any small thing can be measured in this way. But why is it this number rather than something starting with a 1, like 1 times 10 to the 24th, or something like that? Well, the reason might surprise you. For my example, I am going to use the element sulfur, formerly known as brimstone. I think that's a better name, actually. Sulfur is a nonmetal located on the right-hand side of the periodic table, just below oxygen, and it's a little small, so here's a bigger one. 16 is the atomic number, the number of protons. 32.07 is the atomic mass, which is, of course, the mass of one atom, averaged for all the different isotopes and their fractional abundance. So when you talk about the 32.07, what unit is that in? It's not written there, is it? But the unit is very decidedly AMU, atomic mass unit. An AMU is about the mass of one proton or one neutron, very close to that. Okay? It is not the atomic weight. People still use that outmoded term, even though it is definitely not a weight. It is a mass. The only way you could call it a weight is by saying it is a weighted average of the different isotopes. So that is the mass of one atom. Now indulge me here. I'm going to use Avogadro's number now, and then I'll show you a little later where it comes from. Okay? So what if we had a mole of atoms? What would their mass be in AMU? Now we usually don't do this because it isn't that useful, but I'm going to do it. So if we had a mole, it's Avogadro's number of atoms per 1 mole. And then, of course, notice that the atoms are in the denominator on one side and the numerator on the other. So that will make them cancel out. The only way to get rid of a unit is to have it in the numerator and the denominator, and then they will cancel out. So this will give us the number of AMU in 1 mole. So if we multiply 32.07 times 6.02, and then we can write that number, and we'll just keep the exponent because the other one is not in scientific notation. We get improper scientific notation, 193.06 times 10 to the 23rd AMU, and that is the mass of 1 mole in AMU. Of course, to fix the scientific notation, I'm going to move the decimal over 2 places, like so, and then that will raise the exponent by 2. So 1.93 times 10 to the 25th AMU per mole. Now notice I'm abbreviating the word mole by 1 letter, getting rid of the E, to MOL. Now, of course, mole is already an abbreviated form of the word molecule, but we abbreviate it even further as a unit, MOL. So what does this tell me? That's just the number of AMU in 1 mole. We'll get back to this number. See that number? We'll get back to that. But AMU are not going to work. We need to use something we can measure in our laboratory. We need to use grams. The original definition of the gram was the mass of 1 milliliter of water. So if you had 1 milliliter of water, you could measure it, and the mass would be 1 gram. It is also called a cubic centimeter of water. It's the same exact amount, and the mass is 1 gram. In medicine, they call it a cc, which is also a cubic centimeter. They just write it like that. And if you think about it, that makes sense because the density of water winds up being 1. So because of the way they defined the gram based on water, of course the density of water winds up being 1 because you're dividing 1 gram by 1 milliliter, or 1 gram by 1 cubic centimeter, or 1 gram by 1 cc. You're going to get 1 gram per milliliter, 1 gram per cubic centimeter, 1 gram per cc. Also, it works out to be 1 kilogram per liter because you multiply both of them by 1,000, so 1 kilogram per liter as well. So the density of water, of course, winds up being 1. So what does this have to do with Avogadro's number? It has a lot to do with Avogadro's number, because once they determined what the gram was, well, guess how many AMU were in 1 gram? It turns out to be, guess what? Avogadro's number of AMU in the gram. So this is not often mentioned, but this is the true reason that Avogadro's number is 6.02 times 10 to the 23rd. It is the number of AMU in each gram. That's a lot of AMU because they're so tiny. They're about the mass of a proton or a neutron, very close. And a gram is a mass of 1 milliliter of water. So now watch, I'm going to continue with my calculations. So getting back to our previous calculation, you remember that we left off with 1.93 times 10 to the 25th AMU in 1 mole, per mole, okay? But we don't measure AMU in our laboratories. We like to measure things in grams. So what we need is a conversion between AMU and grams. Do you remember how many AMU are in each gram? Oh, that's right. It turns out to be Avogadro's number, 6.02 times 10 to the 23rd AMU are in 1 gram. So you might wonder, well, why am I writing it this way with AMU in the denominator? That's because we need to cancel AMU. So the only way to get rid of a unit is to divide by the same unit, and then the AMU are going to cancel away, and we'll wind up with grams per mole. So then, to get to my answer here, I'm going to take the first portions. I like to do this without a scientific calculator, divided by the first portion of this number will give me this part. And then, of course, it's going to be times 10 to a power. And then to determine the exponent, 25 minus 23, you follow the rules of subtraction when you divide 10 to a power, and you get 25 minus 23. Oh yeah, well, you get 2, okay? And that's the number of grams in 1 mole. But of course, that isn't proper scientific notation. So I got to move the decimal back that way by 1. And if I move it back that way, well, instead of being a 2, it becomes a 1. So then I get 3.207 times 10 to the first grams per mole. But why don't we just write that out the way we often do, not in scientific notation? 32.07 grams per mole. So guess what, guys? That is the molar mass of sulfur. So notice that we went through all this. We multiplied by Avogadro's number to get the number of AMU in a mole. And then we divided by Avogadro's number to get to the number of grams in a mole. So we could have just skipped that whole thing, because if you multiply by a number and divide by the same number, it gets you back to the exact same number you started with, which is why we can use 32.07 in grams for each mole of sulfur, even though on the periodic table that is 32.07 AMU. This number was chosen for our convenience. For once, something was chosen to make our life easier. So we can use that number from the periodic table as the molar mass of sulfur, but just bear in mind that is only because Avogadro's number was chosen for the number of atoms in a mole. So we have Avogadro's number of sulfur atoms, but there's Avogadro's number of AMU in a gram, so it comes out as a wash. It's the exact same number. Boom. So the molar mass is the mass of 1 mole of a chemical. It's when you have Avogadro's number of particles or atoms. And you can see that the molar mass of carbon, well, 12.01 AMU is the mass of an atom of carbon, but 12.01 grams is the mass of a mole of carbon atoms. 28.09 AMU is the mass of 1 averaged silicon atom, and 28.09 grams is the mass of Avogadro's number of silicon atoms. That's a mole. 55.85 AMU is the mass of an iron atom, and 55.85 grams is the mass of a mole of iron atoms. Get it? That's a mole. And that is why we can use the same number on the periodic table on our balances, turning it into grams, because we're multiplying and then dividing by Avogadro's number. So then, if I want to know how many moles of sulfur 50 grams of sulfur is, well, then I need to divide by the molar mass. But the molar mass is so easy to obtain, all I have to do is, I don't even have to use Avogadro's number, actually. I just look on the periodic table and take that exact number, but turn it into grams per mole, 32.07 grams per mole. Then when I divide those, the grams are going to cancel, and I'll wind up with moles. You can see it's going to be a little more than 1. It's going to wind up being 1.16 moles of sulfur. So that's the practical upside. Now remember, if I wanted to know how many atoms of sulfur I have there, I could multiply 1.16 times Avogadro's number. But just knowing how many atoms we have isn't always that practical. A lot of times we just want to keep it in moles. So the point is, we don't always have to use Avogadro's number, but it is intrinsic to the concept of the mole. It's how many atoms you have there. And it's also the number of AMU in a gram. So now you know why that is Avogadro's number, because it's the number of AMU in a gram. Or if I wanted to say this more simply, in short, it's because of the metric system. Bye-bye now.